All right. Hello, everyone, and welcome to Lecture 4 of the Building Planet series, Formation of Earth's Moon. I'm really enjoying giving these lectures. I appreciate your coming. I find it a distraction and a great source of joy and reminder of what's lovely about science in this difficult year. So recall where we left the story in the last lecture, when we were talking about the time from about 5 to about 100 million years after the first solids. Giant accretionary impacts create multiple fast freezing magma oceans on rocky planets, which freeze to form the bottom, freeze from the bottom and produce a dense atmosphere as they freeze. And this implies that rocky planets everywhere may have liquid surface water for some period of time, may be habitable for some period of time. And for this lecture, I'm going to talk about the formation of Earth's moon immediately following the moon forming impact, which was around 4.5 billion years as marked on our timeline now. And so here's today's timeline. We're going to follow the formation of the moon from that moon forming impact around 4.5 through solidification, volcanic activity, and the big impacts of the late heavy bombardment. It'll take us up to about 3.8 billion years ago. There's a lot of action in that period of time. And although we think of the moon as being bright and white, and we'll look at some pictures in a moment where the contrast is very high and it looks like it's white and then also dark, it's actually a very dark gray, the moon is, as shown in this image that was taken by the Lunar Reconnaissance Orbiter camera, which I'm proud to say is operated out of Arizona State University by its principal investigator, Mark Robinson. This image is a kind of a do-over of a famous one that was taken by the astronauts, but this one was taken October 12th, 2015. And it shows, you can look on the beautiful blue Earth if we need a reminder of how precious the habitability of our planet is. And it shows North Africa up there and the Sahara Desert, and also on the left, South America. Now here's the familiar near side of the moon. Pay attention to the dark areas and the light areas, which we're going to talk about next. And by the way, here's the moon's far side, never visible from the Earth, which has many fewer distinctive features than does the familiar near side. This is a fantastic mystery, which is still unsolved, as to why the near side has these huge impact craters and the far side does not. We are not going to talk about that anymore today. I just want to throw it in. So our story today starts with the very first human visit to the moon. Before Apollo, people had a range of ideas about how the moon formed and what it was made of. Some people worried that the surface of the moon was a deep layer of soft, unconsolidated dust, and that the lander would just sink straight in and the astronauts would drown in the dust. So we really didn't know. The Apollo 11, which is what we're looking at here, the Apollo 11 extravehicular activity, which they call the EVA, began at 10:39 and 33 seconds p.m. Eastern Daylight Time on July 20th, 1969. Astronaut Neil Armstrong famously stepped down, and on this, their one and only EVA, the astronauts had a great deal to do in a very short time. They stayed within about 100 meters of the lunar module and collected about 47 pounds of samples, and they also deployed 4 experiments. Now, here's the particular thing that comes into our story. Neil Armstrong collected a bulk sample over a period of about 14 minutes, a bulk sample of the regolith, the soil on the surface of the moon. And by the way, regolith is the word that means soil in the absence of all organic matter. So the powdery, pebbly, rocky, movable material that's on the surface of the moon and Mars and Venus, as far as we know, has no life-derived organic material in it, unlike the soil on the Earth, which is made very largely of organic material. So for a long time, if it was soil, it was really from the Earth. And if it was on another planet or an asteroid, it was called regolith. But a few years ago, the International Association that controls the terminology of soils changed that. And now it is okay to call this soil on the moon. So don't let anyone tell you differently. So Neil Armstrong filled Apollo sample return capsule, the ALSRC, ALSRC, number 1003. People who study the Apollo missions are very obsessed with the specificity of it. Filled it with almost 15 kilograms of material made up of scoops of lunar soil with all size ranges, little powdery bits of dust up to pebbles and little rocks. Some 22 or 23 scoops were taken, and one sieved sample then that was taken out of that bulk sample was given number, Apollo sample number 10001, and another subsample was called 10002. Now, why would I mention that? Because the Apollo samples are all numbered with a starting number that indicates which mission. A starting number of 1 means Apollo 11. Therefore, 10001 is the very first cataloged lunar sample. Some of that bulk sample ended up in the lab of John Wood and his colleagues at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. The photo here shows a little dish of rocks, 1 to 5 millimeters in size, from that Apollo 11 bulk sample. And you can see it says photographed by John Wood. It's actually his photo of the subsample that they studied. Wood and his colleagues described all the rock types that they found in this little sample of lunar regolith, reporting fragments of basalt, which of course is what comes out of a lot of volcanoes on Earth and elsewhere. It's a category of lava composition. This was surprisingly high in titanium, not like Earth ones. Breccias, which is a word that means broken up mixtures. And in this case, they were impact produced. Impacts created these breccias. And also little spherules of volcanic glass, we'll talk more about later. And irregularly shaped smears of glass produced by meteoroid impact. Some of those are called schlieren. And among all these kinds of materials, they looked at 1,676 particles. Among those 1,676 particles, they found just a few, 61, that were something completely different and unexpected. Those particles were white and made up of almost entirely of the mineral anorthite. Anorthite, this was the game-changing moment. So here's a public service announcement. What is anorthite? And what about this word anorthosite? Well, feldspar is the most common rock-forming mineral on Earth, and it occurs on all the rocky planets as well. Feldspar has a sodium, a potassium, and calcium-rich end members, as shown in this triangle. And then you can see that there can be chemical mixtures between the potassium and sodium end members and between the sodium and calcium end members along the bottom. And this bottom series are called the plagioclases. And that's another word that we hear a lot, so I mention it here. When people talk about this aspect of the moon, sometimes they say anorthite, sometimes they say plagioclase, sometimes they say feldspar. But what they really mean is the calcium-rich end member right here, anorthite. This one that is full of calcium. Anorthosite, for that matter, is a rock made of grains of anorthite. And so this is what John Wood and his friends found. They found, and his colleagues, they found grains of anorthosite. In other words, pieces of rock that were made up of many grains of anorthite, the calcium-rich end member of feldspar. Okay, so back to John Wood. He and his team published their results on February 23rd, 1970. Wood et al., 1970, this reference shown here. It was only 218 days after the extravehicular activity on which Neil Armstrong sampled the lunar surface. Wood and his colleagues had effectively solved the problem of how the moon formed in that period of time with that little dish of soil. And the only way, they knew this, the only way that pure anorthosite could form is if that low density anorthite, it's a very low density mineral, crystallized out of a very evolved magma. And in a moment, I'll explain what I mean by evolved, and floated to its surface. And anorthite is almost the only mineral that will float in its coexisting magma. Almost every other kind of mineral sinks when it crystallizes out of its magma. And geochemically, there's almost no other way to make this mineral in abundance. Really, the only way to do it is to have it crystallize and float out of its iron-rich magma. So the moon had to have been molten, and it had to have had a magma ocean. And so this is their picture of their model schematic of this sort of annulus, or really a spherical shell of magma, out of which floated this anorthositic layer. So there it was, 218 days after this was scooped off the moon, the formation of the moon was solved. There was ultra famous Harold Urey, who was in disagreement. He had thought the moon formed cold, but soon the evidence was really incontrovertible. The moon had formed hot. These results and related geochemical arguments spawned a whole field of study, and I was a part of that many years later. Here's a paper from 7 years later, from 1977, where some experimentalists were able to melt an iron-rich magma in a tiny capsule in the laboratory. You can see this is 1 centimeter across, and show that anorthite would float in that magma. So these are the anorthite crystals, those white chunks up at the top of this capsule. And soon scientists were talking about rockbergs, like icebergs, but made of white the white rock anorthosite, floating not in seawater, but in a sea of magma around 1400 Celsius on the moon. So floating rock bergs in a sea of magma on the moon, pretty irresistible. This sample of anorthosite was collected by Apollo 16, and its age has been found to be about 4.19 billion years old. And it was created by floating in the lunar magma ocean. And it turns out that that's what these pale highlands of the moon are largely made of. The highlands of the moon, the white parts here that are higher standing than the dark basalt-filled craters, are largely made of anorthosite that floated in the lunar magma ocean. So then what are these dark rocks in these circular impact craters? Well, this basalt sample was collected near the rim of Hadley Rill by astronauts during Apollo 15 in 1971. And it's one of many, many examples of the kind of basaltic magma or lava that filled those craters and that looks dark to our eyes as we look up at the moon. I want to point out that this particular sample is filled with bubbles. And those really are frozen bubbles that were created by volatile elements that were erupted with this magma. And typically we think of the moon as being pretty dry and volatile free, atmosphere free, but there was something, just enough material that wanted to form bubbles that this one ended up bubbling. This then is the story of the lunar magma ocean, brought about in the first place by the tiny grains of anorthosite that Neil Armstrong gathered from the lunar soil in 1969. Here's where the idea of an evolved magma composition comes in. In the beginning, just like I showed in the magma ocean talk, the lunar magma ocean also is just all one bulk composition. And as cool plumes of liquid magma sink from the surface of the liquid, they begin to crystallize minerals as they sink to higher pressures. And those minerals are deposited at the bottom, as shown with the little solidification point here. The first minerals to form are rich in magnesium and iron, and they're called mafic, Ma from magnesium and F from Fe, the scientific symbol for iron, hence mafic. First, the mineral olivine crystallizes. Olivine is MgFe2SiO4. In that first crystal site, olivine would rather have magnesium than iron. So the earliest layers are magnesium-rich olivine, and all the other elements are rejected back into the magma, whose composition thus evolves. So this is what's meant by an evolved magma. It begins to what's called fractionally crystallize crystals, and then more crystals and more crystals, and each time the composition of the magma changes, it evolves. So after a fair percentage of olivine crystallizes by itself, then olivine plus the mineral pyroxene begin to co-crystallize, and the story is the same. Pyroxene takes magnesium, if it can get it, and rejects iron back into the magma. So the magma gets richer and richer in iron and aluminum and calcium and titanium and a number of other interesting elements. And by the way, another piece of evidence in the long list for the hot moon is this one. The composition of molybdenum isotopes in the moon indicates that its very small metal core formed at a very high temperature. So the moon was almost certainly completely molten. In fact, the moon is the product of shocked molten material flung off of the Earth by the huge impact, an impact that melted both the Earth and the material flung into space, which then recoalesced into the moon, a ball of magma in our sky. Now, this part of the solidification is very fast, less than 10,000 years probably. But at about 80% of solidification, anorthite starts to form, and it floats to the surface and makes a conductive lid on the moon. The magma is so evolved and so iron-rich by now that the high density of the magma encourages floating of the low density anorthite. And as soon as that lid is formed, heat flow out of the moon is much more slow because it has to be conducted through that solid lid. So this final 20% of solidification might take as long as 200 million years. But before it's done, right at the end, a really interesting thing happens. That magma just kept evolving and evolving, crystallizing minerals until all that was left were dregs super enriched with all the elements that do not fit nicely into regular rock forming minerals. Elements like titanium, chromium, and rare earth elements. These dregs are called creep after the scientific symbols for potassium, which is K, the rare earth elements, and phosphorus, which is P. Traces of this highly unusual material are found in volcanic rocks on the moon. So in summary, here's what happened on the moon. First, on the top left, molten above a solid center or possibly no solid center. Solidification occurs from the bottom up And then at about 80% plagioclase, that is anorthite, begins to form and it floats to the top of a now internal magma ocean. And then finally solidification is complete. But look at this curve that says tidal heating. Once there is a solid anorthosite layer over the shell of remaining magma, the gravitational interactions between the moon and the earth create flexing in that solid shell and significant heating from friction. This is tidal heating. This heat slows down the cooling of the moon and may make that cooling last as long as 200 million years. This was a great thing to calculate since it solved a mystery about lunar samples that we'll get to in a moment. Also, remember that the moon formed probably only 6 Earth radii away from the Earth. Now it's over 60 Earth radii away for comparison. So check out, by the way, the amazing, beautiful short story, The Distance of the Moon by Italo Calvino in his collection Cosmocomics. It's a story inspired by the ancient close-up moon. I really love that story. So this is a little gratuitous, but I couldn't resist showing a few photomicrographs I made of Apollo 15 soil samples using Tim Grove's electron microprobe at MIT when I was in grad school. This is sclerin. This is a material that was melted and mixed together by meteorite impacts. And look at the scale bar at the bottom, 700 microns. If you can see it, that black bar, that's 70% of a millimeter, so very small. And here's an amazing thing, a bead of volcanic glass, a bead that started as a liquid droplet shot out of the moon when it was volcanically active, long after the magma ocean was solidified. These volcanic fire fountains spewed perfect little glass beads all over the moon. And these are like windows into the temperature and composition of the interior of the moon at that time, between 3 and 4 billion years ago. Here's another glass bead that before it froze in the cold of space, quickly grew crisscrossing olivine crystals. Very beautiful, I think. And here's a third, which was spinning as it flew and it stretched into a dumbbell shape before it froze. Now, because of the heat of formation and the violent physics of impacts, people assumed that the moon was formed completely dry. This was because of our bias about what it's like on the surface of the Earth. Extremely hot things drive off their liquids. We don't have a lot of intuition for the kind of physics that formed the moon. And then in 2008, Alberto Sol measured some of these little glass beads for water and found they actually had traces of water in them. That meant that the interior of the moon formed with traces of water. That meant the moon was not perfectly dry. So what do we mean by not perfectly dry? Some of the press at the time made it sound like there were rivers and oceans on the moon, which there were not. So what do we mean by not perfectly dry? Well, here is a graph that shows on the vertical axis an amount of water, or hydroxyl, which is OH, in parts per million by mass. And so 1,000 parts per million is 0.1%, for example. And so the lunar volcanic glasses, shown there in the darker green, just have tens to even up a little higher hundreds of parts per million of water. And at the very top, there are tiny little apatite grains that might even have fractions of a weight percent of water in them, very small amounts. However, there's another way that the moon is wet, and that is on its surface. The solar wind drives protons onto the surface that steal electrons and bind with oxygen and make hydroxyls in water. And then comets and asteroid, rocky meteoroids hit the surface of the moon and add water. And that water can be saved for the age of the moon, more or less, if it falls into or hops into these permanently shadowed craters where the sun never strikes, and so the water never gets remobilized. And some of those shadowed cratered soils might have 4 or 8% of ice in them or more. We're not sure. So how wet is that? Well, look at the top right. The typical range of sandy desert soil moisture on the Earth is about the same as the wettest parts of the moon. And those measurements are from the Sahara Desert. So very, very dry. Turns out the surface of the moon is very, very dry. Interestingly, if you look at the red stars, those are some good recent estimates of how much bulk water the moon might have. And the Earth has maybe 10 times as much, but neither the moon nor the Earth are really dry. They're both a bit wet, which is exciting and relatively new science. So finally, let's put this all together. Here's a timeline from 3.2 billion years ago back to 4.567, the age of the first solids. And you can see the moon forming impact around 4.5. Then there's the anorthosites, and those are the ages at which people have measured that they formed. And they formed over about 200 million years. And so discovering that the moon, in fact, probably stayed molten because of tidal heating for 200 million years helped to solve that problem of how long it was that anorthite was being formed. Then there were a couple of other suites of volcanic and igneous rocks that are found, the MG suite and the alkali suite. And then those basalts start forming, the ones that are in the end filling these craters and found elsewhere on the moon. And they continued for a long time. Some people think past 3 billion years ago, almost up to 2 billion years ago. The moon was volcanically active. We could have looked up and seen volcanoes on the moon, which I love. And so here are the major near-side impact craters labeled with their names, along with the 3 Apollo mission locations that I mentioned in this talk. This is the last step I have time to talk about today, the formation of these huge craters. So these impact basins all date to a relatively short time period between 3.8 and 3.9 plus or minus billion years ago. You can see here the ones that have been dated. I've drawn lines and show them in green and blue and orange. That period is known as the late heavy bombardment. And by the way, it almost certainly affected the Earth as well. There's almost no way it didn't. And also the other rocky planets. We think it might have been caused by interactions between Jupiter, Saturn, Uranus, and Neptune that caused Uranus and Neptune to move outward into a population of small bodies that was contiguous with the present day Kuiper Belt where Pluto is. The big planets would have scattered those small bodies inward, and by being scattered for such a long distance, speeding up as they come toward the sun, they would have hit the moon and the other terrestrial planets with great energy. So that's the late heavy bombardment. And so finally, here's our timeline from today. The moon started as a molten ball coalescing out of the splash from a giant impact with the Earth, as first shown by this dish of lunar soil. And that allowed us to determine how the moon solidified with this floating anorthosite lid. And from the time of its formation to perhaps 2 billion years ago, the moon had volcanoes that put lava flows, basaltic lava flows, and glass beads into its surface. And then also between 3.9 and 3.8, more or less, all the rocky planets experienced the late heavy bombardment, a huge series of impacts thrown at us, we think, from the outer solar system. Thank you so much.